Welcome to Graphing Logarithmic Functions. It's just going to be a quick video. I'm going to do 3 problems from a packet of 8. This would be an option. If we knew exactly what y equals log base 2 of x looked like, all we'd have to do is shift everything to the right 3 and down 2. But until that, here's a pretty good method, particularly when we get into more complicated ones like when I go through number 6 momentarily. So I'm going to do, it's just kind of educated t-charting. I call it rubber stamping, and I'll explain why shortly. But I'm just going to go through the process that if we were going to just be t-charting, we'd choose a value for x, then we would subtract 3, then we would take log base 2 of that, and ultimately we would subtract 2. The whole key to this is I don't really want to choose values for x. Because if I choose, say, x to be 8, then I get log base 2 of 5. That's the exponent that turns 2 into 5. I don't know. I want to choose values for x minus 3. Like I might want x minus 3 to be 8. Because log base 2 of 8 is the exponent that turns 2 into 8. That's 3. So here's what I do. I wait, and I'm going to choose a value for x. I'm going to subtract 3, take log base 2, and then subtract 2. But I'm not really going to do that. I'm actually going to choose a value after I've already subtracted 3. And I want this row to be convenient powers of 2. I'm always going to use these values. 1/2, 1, 2. And then beyond that, I might use 4, 8, 16, etc. powers of 2. For instance, if this was log base 3, I would use 1/3, 1, 3, 9, 27, ... If it was log base 7, 1/7, 1, 7, 49, etc. Okay, then log base 2 of 1/2 is the exponent that turns 2 into 1/2. Turns 2 into 1/2, negative 1. The exponent that turns 2 into 1 is 0. The exponent that turns 2 into 2 is 1. 2 into 4 is 2. 2 into 8 is 3, 2 into 16. We'll just go as far as we need to. You'll always probably want to use at least those first 3 values. Then after I'm done with log base 2, the next thing I do is subtract 2. So subtract 2 gives me negative 3, negative 2, 1 minus 2 is negative 1, and 2 minus 2 is 0. Now, only slightly tricky to get from row A to row B. If I would have chosen a value for x, I would subtract 3. So to go back, I need to inverse operation, add 3. I get 3.5, 1 and 3, 4, 2 and 3, 5, 4 and 3, 7, and we see 8 and 3 would be 11, but that takes us off the graph, so we don't need those. And now we've got 4 nice ordered pairs. Start with 4, end with negative 2. Start with 3.5, end with negative 3. And if I use those in conjunction with the fact that there is no exponent that can turn 2 into 0, in other words, x minus 3, I can't have x minus 3 be 0. So my cutoff is 3. That's actually the asymptote. So I've got an asymptote at 3. A nice quick check here on how we're doing is this value should be very close. This first value we produce should be very close to the asymptote. So we have a point at 3.5, negative 3. Sure enough, it's close to the asymptote. And then we have a point at 4, negative 2. I go over to 5 to get to negative 1. And I have to go over to 7 to get to 0. And here's something on my graph goes all the way down, follows this asymptote. And here's something I'm going to be picky on. I just call it the soccer goal exit. In other words, I know my next point would be, if I went, just for instance, if I went to 8 here, then the exponent that turns 2 into 8 is 3. Subtract 2 from that, I'm at 1. Add 3 to that, I'm 11. My next point over would be 11, 1. So I have to exit between here and here. And we're so close, it was pretty common sense that we would, but sometimes that's going to be a little tougher decision. So I'm going to be really picky about where you exit the graph. Okay, let's take a look at one with fractional base. I'm going to choose a value for x. I'm going to subtract 1. I'm going to take log base 1/2, and I'm going to subtract 5. Now the first thing we might want to do is just note that x minus 1 may not be 0, so x cannot equal 1, or x equals 1 is a vertical asymptote. Then, after I subtract 1, I want to have convenient powers of 1/2 here. Now, I treat 1/2 or fractions just like I treat it if it was a reciprocal, just as if it was 2. I want this to be 1/2, 1, 2, 4, etc. What is the exponent that turns 1/2 into 1/2? 1. 1/2 into 1, 0. 1/2 into 2, it has to be flipped, so it's negative 1. 1/2 into 4, it has to be flipped and squared, so it's negative 2. If I went to 8, it would be negative 3, etc. Then I subtract 5. 1 minus 5, negative 4, 0 minus 5, negative 5, negative 1 minus 5, negative 6, negative 7, negative 8, if we need to be there. And now, again, the part that messes people up, I'm not subtracting 1 to get back. I subtracted 1 to get from A to B. I need to add 1 to get back, so 1 1/2, 2, 2 and 1, 3, 4 and 1, 5, 8 and 1, 9. We're off the graph. So I have a nice point, 1 1/2, close to the asymptote. It's a good check. 1 1/2 gets me to negative 4. 2 gets me to negative 5. 3 gets me to negative 6. Now, if I tried to just guess at what the graph looked like, I might not know where it exits, what hockey goals it goes to. So I continue on. 5 gets me to negative 7. And even now, if I didn't know this next one, I might not know, does it exit through here? Does it exit through a hash mark? Does it exit below? So if I went to 9, I would just be down at negative 8. So my graph hugs along the asymptote. And then if it takes over to 9 to get down to negative 8, it must exit somewhere between here and here. And again, I will be picky on that. Okay, one more. This one's a little bit uglier. We're going to just have to trace things. We got some more things going on with the function. I would choose a value for x. I would multiply it by 3. I would add 15. I would take log base 2, and I would subtract 3. After I'm done finding the argument, adding 15, last step, I want convenient powers of 2. 1/2, 1, 2, 4, 8, etc. We're going to find out we need a number of them here. I can't tell that necessarily based on inspection, but I've done this problem before. So the exponent that turns 2 into 1/2, negative 1, 2 into 1, 0, 2 into 2, 1, 2, 2 into 8, 3. Subtract 3, negative 4, negative 3, negative 2, negative 1, 0. Backwards. Here's where people get messed up when there's 2 steps. To get from A to B, I multiply 3. B to C, I add 15. So C back to B, I have to subtract 15. Not the most convenient. Negative 14.5. Negative 14. Negative 13. 4 minus 15. Negative 11. 8 minus 15. Negative 7. And to get from A to B, I multiplied 3. So to get back there, I have to divide 3 or multiply by 1/3. In some cases, that's easy. Negative 14 thirds, negative 13 thirds, negative 11 thirds, negative 7 thirds. In this case, I'm going to make this improper. Negative 14 and 1/2 is negative 29 on 2 times 1/3, negative 29/6. Not the prettiest value. Okay, we should note that 3x plus 15 may not be 0, so x may not be negative 15 divided by 3, negative 5. There's our asymptote. Now, negative 29/6, is it close to negative 5? Well, negative 30 on 6 would be negative 5. So yeah, we're really, really close. Negative 29. Here's negative 36, so just 1/6 over gets me down 4. So right here, down 1, 2, 3, 4, practically on the asymptote. Negative 14/3. Excuse me, I'm just going to count by thirds. 1/3, 2/3, 3/3, 6/3, 9/3, 12/3, 13, 14/3. I'm still really close to the asymptote. Gets me down 3. Negative 13/3. That's just 1/3 shy of here. Just barely making horizontal progress at all. Negative 11/3. 3, 6, 9, 10, 11 thirds. Gets me down to negative 1. And negative 7/3. 3, 6, 9. There I started to make a move. 3, 6, 7/3 gets me to 0. But I have no idea where this is exiting. So I'm going to continue on. I'm going to do at least 2 more. I'm going to go 16 and 32. The exponent that turns 2 into 16, 4. 2 into 32 then must be 5. Subtract 3, 1, and 2. Subtract 15, 1, and 17. Divide 3, 1/3, but 17/3. Now we're making some horizontal progress. Let's plot those. At 1/3, we're up at 1. At 17/3, well, let's see, 3, 6, 9, 12, 15, 16, 17/3, I'm up to 2. We hug along the asymptote. And it's pretty easy to tell if that step, if I went over 5, my next step's going to take me off the graph. So here's my soccer goal. We're going right through there. Have to exit the graph in an appropriate location. Okay, that should be enough. If you might need to replay it, take a look. I will tell you 7 on this worksheet, probably the next most challenging problem to number 6, but there's a lot going on number 8 as well. So pretty mechanical. The reason I call this rubber stamped is because a log base 2 graph would always include at least that. And like I said, if I had a log base 7, it's just basically a little bus. If I had a log base 7, it would always at least include 1/7, 1, and 7. Maybe 49, ... but at least would include those. Okay, and that would just be negative 1, 0, and 1. And that, if I have a rubber stamp, just to stamp it on there, I could build my graph around that little bus shape all the time. Okay, hope that's helpful. Good luck to you. Let me know if I can be of any assistance.